Hello, myself Dr. D.K.Shedge, Professor in Electronics and Telecommunication Department, AISSMS Institute of Information Technology. Today we'll discuss about R-2R ladder digital to analog converter, that is the DAC. R-2R Ladder DAC have got many applications, but R-2R, why it is named as R-2R? Because R-2R ladder network is formed before 741 IC. This is actually one of the I to V converter. Here, two values of registers are required. That is, one is R and other is 2R. And this circuit is taken very simple circuit for only 2-bit D to A converter. Same thing can be applied for higher number of bits also. The typical value of feedback register here is taken to be 2R. Let us say analysis of this for only 2-bit converter, then similarly will get applied for the higher number of bits as well. Here B0 is LSB and B1 is MSB. Rightmost is the MSB, leftmost is the LSB. The analysis of this circuit can be seen by applying a superposition theorem. That's why we'll apply only for one of the input and the other for other input. Just similarly, it can be found out. The circuit can be analyzed very similarly. Here we need to find out only voltage coming at node A, which is shown by capital A, node A, so that the output voltage will become voltage at node A multiplied by gain of this inverting configuration. 2R divided by R, gain will be minus of 2. Purposely here input is taken to be negative. Whenever minus of VR is applied, it is said to be logic 1, and whenever ground voltage is applied, it is said to be logic 0. As we are using the inverting amplifier in R-2R D to A converter, that's why we took input to be negative. You can say negative logic. The operation of above ladder can be explained with the help of taking the ideal characteristics of operational amplifier. The ideal characteristics of operational amplifier, that virtual ground concept. Pin number 3 is connected to ground. That's why potential at pin number 2 also will be 0. So we can show there a 0 potential or a ground potential at pin number 2, and hence we can replace the equivalent circuit just like passive network. 2R and R will be coming in parallel, forming a resistance of 2R into R divided by 2R plus R. That's why 2R divided by 3. Node A kept intact, then register of R, and here we assume that we have applied only B0 and B1 is 0, B0 is 1, B0 is logic 1, B1 is 0. So B0 is minus of VR and B1 is 0. That's why grounded we had shown here. Then we can apply here nodal equations, that is using Kirchhoff's current law. Equation at node A we can write here. So equation at node A in this simplified circuit diagram we can write the current entering equal to current leaving. VA divided by 2 by 3R, we can say current leaving, plus VA minus VB divided by R, VA minus VB divided by R equal to 0, or algebraic sum of currents at node A equal to 0. This we can simplify 3VA upon 2R plus VA minus VB upon R. So we can take LCM to be 2R, and then numerator simply will get 3VA plus 2VA minus 2VB divided by 2R equal to 0. So 5A equal to 2VB will become the numerator, and VB will become 5VA upon 2. Similarly, we can apply KCL at node B. At node B also algebraic sum of currents equal to 0. We can apply Kirchhoff's current law. So we can write the equation there, VB divided by 2R plus VB minus, because we are applying a reference voltage to be negative, minus VR divided by 2R plus VB minus VA upon R equal to 0. So we can take once again LCM to be 2R, and we can write VB plus VB minus plus VR plus twice VB minus twice VA equal to 0, and then numerator will become equal to 0. Denominator term will get multiplied on right hand side. So 4VB plus VR minus 2VA equal to 0. VA plus twice VB, VA equal to twice VB plus VR by 2 will become expression for VA, and we can substitute VB from earlier equation where we had applied KCL at node A for VB. So we can find out VA equal to, we'll get VA equal to minus of VR by 8. As expected, we are applying here a negative potential as a VA, and that's why then the output voltage corresponding to only LSB set in case of 2-bit D to A converter will get minus of 2R upon R multiplied by VA, or minus of 2R upon R multiplied by minus of VR by 8 will become VR by 4 as expected in case of 2-bit D to A converter, because the LSB will have weightage of VR divided by 2 square as it is a 2-bit DAC. The MSB will have weightage of VR divided by 2 raised to 1, that is a VR divided by 2. So only one thing we work out similarly can be worked out for the MSB set, which is B1 equal to 1 and B0 equal to 0. Similarly, it can be calculated for 3 combinations of digital inputs. Then we'll have here 8 number of combinations, and then weightage of LSB will be VR divided by 2 raised to 3. That is, it will be VR divided by 8. This table is given for only 2 input D to A converter. That's why weightage of one LSB is VR by 4, and then whenever your digital number will be incrementing by 1 LSB, the output analog voltage will get incremented by VR by 4. The advantages of R-2R ladder D2A converter. R-2R ladder D2A converter contains only 2 values of registers. That is, the variety of registers are only R and 2R. As compared to the binary weighted registers where we require the variety of registers, here we require only 2 values of registers. If more number of bits are present in the digital input, still will require only R2R combinations, but more number of combinations will be required. Due to this advantage, R2R ladder is preferred over the binary weighted register DAC. Thank you.